instruction fetch unit real quick. This is the very first part of any computer um, execution, because obviously you need instructions to execute for the computer to do anything. Let's just jump right into the diagrams. So this is a high-level diagram of how iFetch unit works. The right part of this we already covered in a previous video talking about caches. This is just basically saying I'm going to look up tag and data array and then also look at the TLB. The only thing here is in the discussion of virtual versus physical addresses, the assumption here is that the index is virtual. So even if the index is virtual, then you can go ahead and spit out a physical tag that you can do a physical tag lookup with in the tag array. So you're going to translate from a virtual, aka software index, and then from the TLB, that mapping will spit out a physical or hardware tag that will be grepped against this hardware tag array. And then once you have a tag hit, then you can go ahead and then inform which way of the data cache to pick, so then you can actually spit out your data and align it. For the left-hand side is kind of where they're all part of the instruction fetch. So the right-hand side is the cache portion, and the left-hand side is the prediction portion. And there's a few structures here. The next sequential fetch address is just if you're executing program order, this just increments and say, well, here's your next instruction. Branch target buffer is just basically saying if you, let's say, have an if-else statement or a for loop, while loop, or perhaps in some implementations a function call, it'll say, well, I predict from our current program counter PC address, we're going to jump to some, distant address relative to my current address based on taken or not taken in a branch. And then branch predictor, basically, I guess here is to select between, hey, if I'm not taken, I'm just going to get this next sequential fetch address, and then this branch target buffer. I guess I misspoke. This branch predictor predicts taken, not taken. This just keeps all the taken addresses, meaning you take the branch and then you jump somewhere else. This says not taken, and then you just continue sequential execution. This branch predictor predicts taken or not taken, which you choose between your taken address and not taken address. And then your address, the bottom line is that it gets spit out, right? And then you execute it on the right-hand side. Return address stack, pretty common nowadays in CPUs, is for function calls. So, so like if you have, let's say, function A calling function B, which then calls function C, then this is a last in first out, and then it would just kind of pop out of stack. So then when you return from, like, let's say your lowest level function, then you're going to go ahead and pop back up into a previous call, like in your call stack. And then since it's a LIFO, it just conveniently works out that when you return back to the previous function, then you're just going to get the 100% accurate address. So I mean, you could think of like DFS or recursion, where you have a lot of deep function calls. So this would be somewhat okay for that, because then the deeper you go, the bigger your stack is. But then once you get to your base case, start returning, the stack would have memorized where all the addresses of all the different calls are. But in practice, recursion isn't a great way to implement code. Great for interviews because it's more terse, but very bad for performance, because a lot of times return address stacks are not that deep, like tens of entries. And because of that, if you do return address and you have a depth of like 250 in your DFS or recursion, then you're going to just overflow your return address stack, and you start mispredicting and taking a lot of penalties. And a lot of penalties means much lower performance. So that's that diagram, which describes, I would say, 80% of the chapter already. This is just saying how memory is organized in some different forms of iCache. I don't think it's that important. This BTB talks about basically you have a PC where basically where your program is currently being executed, and then you hash it to generate a tag lookup and target address. So for example, in address 3, you might call a function, I don't know, like get sum, right? But then get sum could be an address 1000. Then this target address will be relative to this PC, or 997 decimal. So like 3 plus 997 will give you the address you should jump to. You could also do absolute address, but I think in here it says PC relative. Return address stack we already talked about. Conditional branch prediction is talking about if-else statements. Here is a perceptron, which is basically a saturating counter. If you can, let's say at machine reset, just predict not taken, but then if a branch takes a bunch of times, like let's say 4 times in a row, then you're going to predict taken. And if it's kind of less than this kind of perceptron, half of this perceptron, meaning that the MSB is 0, then you're going to predict not taken. So this prediction is basically, you can look at this prediction table as like, hey, here's a PC, and then these LSB of n bits, excluding byte offset of the PC, is going to map to a table, right? And this table is just going to be, so every single entry of this table will be this FSM, perceptron FSM, where you predict taken or not taken based on past history of actually taking or not taking, right? So this is a very tiny, like, basic sort of machine learning thing that you can do with every single address that has a branch. There might be aliasing issues here though, because if the MSBs of the PC matches, right? And then so if you are aliasing a bunch, which normally doesn't happen too much because things are sequential, but if you alias a bunch, then you know these will thrash on each other. And then here it talks about a combination of this is called a local branch predictor. Local meaning I have a local address, and then I want to see what the target address is, or predict what the target address is. And then here, there's some global branch history, and with a local address, and then they both combine to create a hash. You create a taken, not taken. All the information you're adding here to the hash is the global branch history, which is just saying like on the global level that's not particular to this specific address, right? Because previously it's a specific address mapping to whether or not that specific address is going to be taken, not taken. This just includes global history of taken, not taken. So it doesn't matter where your program execution is. This is going to be a bunch of streaming ones and zeros of taken, not taken. As branches are being encountered, it will be a hash with this PC, and then now your hash basically combines information of some local PC branch information as well as like what the global state of things is. So you can kind of think of this, you know, as like a macro sort of economics versus like a micro kind of business fundamentals kind of thing to generate, to kind of use both pieces of macro and micro information to create a taken, not taken sort of situation. This is just saying this diagram is just this diagram, except you have a lot more global branch histories based on different PCs. But I don't think that's super duper important. I think it's just a high level concept. Here it's a hybrid branch predictor. So a predictor 1 could just be a very local predictor like this first one, and then predictor 2 could be a global correlation predictor that takes into account both global and local address, both global history and global and local information in predictor 2. And the reason behind that is because with a local predictor, actually let's see what this says here. Yeah, a local predictor has a short warm-up time because you only have a saturating counter of like 4, and then for each local address there's really only one entry associated with it. But if you also have to do a combination of global history and PC, let's say the PC was cardinality of like 10,000, and then global history was cardinality of like 100. Well, if you need to combine both, then the global history is combining both is about 100 times more addresses than the local prediction. So combining piece like local and global information is going to take a lot longer time to warm up because there's just a lot more addresses to saturate. So what you can do is just basically saying like, hey, let's look at the yeah, so you could probably just like have something where you select right after a context switch, because if you switch threads, then all the addresses are going to be wrong. After some warm-up time, the correlating predictor will start predicting better than the local one. So now instead of having this counter where this counter is taking into account what was actually taken and not taken, this selector between two models of prediction can also just be a saturating counter, where it says, instead of what was actually taken or not taken, you can say, well, which predictor was actually right? So this could be a perceptron on the two predictors, and then you just choose which predictor is more right. And then that's kind of how you implement it. It's kind of meta, because then this is just basically a perceptron of the two predictors. The local predictors is perceptron of taken, not taken, and predictor 2, which is also a perceptron, but then you just span out to a lot more addresses because you have to combine both local and global history. I think that's the end of this chapter. So that's how instruction fetch works.